Okay. So we've got a few things to do today. Quite a few things, actually. It's all to do with sequences. But before I get into the material itself, I need to talk with you guys for a minute. I mentioned the other day that I had something of a cheating scandal in one of my other classes. And well, I'm happy to say that upon review, you guys weren't as bad. But I know a bunch of you guys cheated on that test. I don't know any nice way to say it. I'm not the sort of person to bullshit. I don't want to be a reductionist, but I know what it looks like when someone is learning this material. I know what it looks like when someone has mastered this material. I know what sort of graphs human beings draw versus calculators. And I know what sort of steps human beings can skip in their head. And when I see things that are not those things, I want to give the benefit of the doubt. When I see those things on many questions, I have a little conversation with myself, and it usually goes something like this. If I start a conduct trial, that's going to screw this person over for a long time, especially if Dan Rodkin ends up pushing for a ZF. Because that makes it not only, harmful here in the sense that you fail the class and you have to deal with some other sanctions, also makes it very hard to transfer somewhere else. I don't like doing that. But sometimes it's necessary. So I just want to say this, and you can talk to other people who've taken classes with me or look on my Rate My Professor or whatever. I can tell when you're cheating. You might think that in the online setting, it's harder to tell, but it's really not. I understand that in the online setting, it's much more tempting because there's nobody right there watching you. And, it's online. So like you're already online. So tempting to use outside resources. I know that HonorLock is overzealous, flags a lot of things that don't deserve to be flagged. So I can't really trust HonorLock's flagging system, but I can trust their videos. Y'all's cell phones are bright. They shine light up on your chin when you look down at them. And all the stuff I said a second ago about what human work looks like as it's actually done versus what work looks like when it's copied from a non-human source like Symbolab, Photomath, or wherever else, Wolfram, all that shit. This is the one and only warning. I know a bunch of folks did cheat on that test. I can tell. There might be some cases where people cheated and I couldn't tell. That's possible also, but there were definitely a handful of cases where I could. This time, I'm not going to do anything big about it. If I see it on test 2, test 3, or the final, it will be a conduct trial. I won't even think twice about it. I'll just send the shit to Dan Rodkin and we'll proceed with the conduct trial. I don't like doing that. And I'm sympathetic with the fact that on the online class, it's so much more tempting. So that's it. That's all I'm going to say. You guys did not cheat as wildly and offensively as one of my other classes did, and I appreciate that. But there was definitely still some cheating here, and I just want you to know that I see it, and that the only reason this isn't coming down like a hammer on you right now is because I'm choosing not to. And I will not do that again. So please, exam 2, exam 3, the final, I want to see your work. I want to see what you can do. And I just want to see that. Even if you're not sure if what you're doing is right, just start writing stuff down. Write down what you think would work. Give me some idea of what you know. And I'll do everything I can to find partial credit for you, I promise. Most of the time, if you take two students who are both underprepared, say prepared at approximately the same level, but neither quite ready, one student tries to cheat to hack together extra points. The other student diligently shows everything they know, even though it's not all there. The cheating student usually does worse because you burn time looking at stupid shit that's not relevant. You write down stuff that you don't fully understand and doesn't connect to the problem. Whereas the student who just shows me what they know, even though it's not all perfect and not all there, they'll have some cohesive ideas on the page. Now, maybe they get stuck somewhere. Maybe they make a few mistakes that end up losing points, or maybe they don't get full credit because they don't finish the problem. But they still end up getting more partial credit than the student who cheated 9 times out of 10. There were a handful of cases here where I was like, okay, this is pretty obviously cheating work, but it's correct. And it's relatively thorough. I didn't do much about that here. But in the future, it's going to be an immediate 0 on the test, an immediate referral to Dan Rodkin and conduct trial and ZF in the class, which is not good. You really don't want that. And I don't want that. I don't want that for you. I understand how tempting it is. I get that this situation is difficult, and I want to work with you in every way I can that is fair. And needs to be fair to you, needs to be fair to me, needs to be fair to your peers. So if you're feeling underprepared or if something's not going well, talk to me. And then even if you're feeling underprepared when you sit down the test, just do your best and show me what you know. And I promise I'll work with you as much as I can. If you're feeling nervous, I want to give you an example. I had a student over the summer in this class, Calc 2, who had the background knowledge and had the skills, but didn't have the discipline, and then had some family issues, and then got sick and just consistently fell behind and bombed the first couple tests. He contacted me before the 3rd test and said, I'm not at all ready and I don't know what to do. So we set up a completely different timeline for him. Let him finish the class about 3 weeks after the rest of the class. He took an incomplete for that class. We set up a separate timeline for him, and then he was able to start back where he had kind of fallen off the wagon, pick it back up there, and start moving through. I'll do that for you guys too if you're in a situation like that. So please contact me, work with me, but don't lie to me. Don't try to cheat. All right, that's it. Enough of that. And if you weren't cheating on this test, please ignore everything I just said. But I know that some folks did, so that is to them. Today, now that I'm done sitting down and talking to you like a grumpy father, we're going to talk about more sequences. Specifically, today is very theorem heavy. So at the end of class last time, I encouraged you to read section 11.1. I did that because there's a shitload of theorems in there. And theorems are the sort of things that usually you want to read and look at a few examples, and then read again and look at a few more examples, and then try to use. The first one is kind of boring. These are limit laws. And they're the same as they are for limits of continuous functions. So if an and braces bn are sequences, and remember, these curly braces just mean rather than referring to the nth term of the sequence, I'm referring to the whole of the sequence as a single thing. Then the following things are true. The limit as n goes to infinity of an plus bn is equal to the limit as n goes to infinity of an plus the limit as n goes to infinity of bn. Right, so if your sequence is made up of 2 pieces added together, you can take the limit of each of those pieces and then add them up. And this is something that everybody does intuitively anyway. But this theorem tells us that it's okay to do that. And if the plus is a minus, you've got two pieces subtracted, you can take the limit of each and subtract them. It works fine. Limits play nice with addition and subtraction. They also play nice with multiplication. So if your sequence is made up of two pieces that are multiplied together, and maybe altogether you can't see what the limit is, but you can see what the limit of each of the individual pieces is, you can take the limit of each of those individual pieces and multiply them. That's fine. If it works for addition and subtraction, and it works for multiplication, probably works for division. And it does. But here there's one additional catch, and you can probably guess what that is. The limit of the sequence downstairs, if you're going to handle it this way, needs to not be 0. So if your sequence is made up of a fraction, you have the option to try taking the limit of the top and bottom separately. When you do that, your result will be useful only so long as the limit of the bottom is not 0. If the limit of the bottom is 0, then you probably shouldn't split it up like this. You should probably try something else. There's one more that goes along with this. Really, I guess two more. The first here is that if you have a constant times your sequence, you can pop out the constant. And then if you have some stuff all raised to a constant power, you can stick the limit inside. Right. So these should look familiar. They are literally the same as the limit laws you learned for continuous functions at the start of Calc 1. And the theorem here just says, yeah, that shit works great for sequences too. In fact, you could take this theorem to be a consequence of one of the theorems we talked about last time, where if your sequence is dots along the graph of some continuous function, then the limit of the sequence is the same as the limit of the function. Therefore, all of the rules for limits of functions apply to sequences. But it's nice to write this out explicitly. Your textbook does it, so why not? There's one more theorem along these veins, and several of these pieces could be taken as special cases of that. But this also extends to other things. If f of x is a function continuous at x equals L, and the limit as n goes to infinity of an, your sequence, is L, then the limit as n goes to infinity of f of an. So you form a new sequence by sticking your old sequence inside this continuous function. Or maybe someone hands you a sequence that you can understand as a easy to work with sequence stuck inside a continuous function. Then you can shove the limit inside. So compare this to item 5. We know that power functions are continuous, right? Like x squared, x cubed, x to the 4. This says that you can shove the limit inside the continuous power function. And what this theorem does is it generalizes that. It says you can shove the limit inside any continuous function, not just powers. In some slightly more grown-up math classes, the theorem at the bottom is taken to be the definition of continuity at L. that for any sequence converging to L, you can shove the limit inside and get f of L out. So I'll give you just a second to get all this stuff written down in case you haven't done. And then we're going to get a little bit of practice with it. Anybody still writing?
Yeah, just 1 second.
Yes, yes.
Sure, of course. Yeah. Let me know. I'll ask again in just a second. If you still need another second, let me know. Okay, anybody still writing?
Good.
All right, I'm gonna go ahead and move on. So let's investigate the convergence of the sequence an equals the square root of n plus 1 over n minus 1 over n squared. So remember what it means for a sequence to converge or diverge. It's all about the limit of the sequence. So what we should do here is take the limit of this sequence. And then if we get a finite number out, the sequence converges. If the limit doesn't exist or is infinite, then we get a divergent sequence. So my first step here is just to write down the limit. The limit as n goes to infinity of an is the limit as n goes to infinity of the square root of n plus 1 over n minus 1 over n squared. Now, which of those limit laws can I apply here?
The one about powers, so you could
Very
pull that.
good. Yeah, exactly. This is the same as the limit as n goes to infinity of n plus 1 over n minus 1 over n squared, all to the 1/2 power. So I can shove my limit inside that 1/2 power. And I get paren lim n to infinity n plus 1 over n minus 1 over n squared, all to the 1/2. And now within those big parentheses, I've got this difference. So which one of the limit rules can I use from here?
Subtraction.
Good, right? That very first one said, okay, well, if you've got a limit of a difference, that's the difference of the limits. So that's lim n plus 1 over n minus lim 1 over n squared, all to the 1/2. And from here, now we can use stuff that we learned on Wednesday. On Wednesday, I taught you what you need to calculate this first limit and what you need to calculate this second limit. The second limit here, the 1 over n squared limit, what is that and why? As n goes to infinity, what does 1 over n squared go to?
0.
Good. Why?
getting smaller and smaller.
That's true. We had a specific result that we can refer back to here, though.
Is it because the power is greater than 1?
Not greater than 1. So don't confuse the result on sequences with the result on p integrals. Remember, limits like this, limit 1 over n to the p, this will always be 0 if for any power p which is positive. So remember, this was one of the theorems, or one of the results on sequences that we discussed right away. 1 over n to some power as a sequence, that will always go to 0. It's very important. I know this is tricky, but it's very, very important that you keep straight in your head the results for integrals, sequences, and series, all different. So here, 1 over n to the p goes to 0 because the power is positive. In other words, if the n squared really belongs downstairs, if the n term really belongs downstairs, i.e. this power isn't negative, which would bring it back upstairs, then 1 over n to that power will always go to 0. This is like 1 over infinity, right? N to the p, as long as p is positive, goes to infinity as n goes to infinity. So this would be 1 over infinity, which is 0. What do I need to calculate this piece? There was a name for the trick that we talked about, which would be useful here. I called it the most important result in sequences. Single most important trick. What is it? Starts with an R. Not recursive. Recursive sequences are like where you have initial conditions and then a recurrence relation. It was before that. What did we talk about on Wednesday before then?
Renormalization.
Very good. I can renormalize this piece. So I divide top and bottom by the largest power of n that we see anywhere. The largest power of n that we see anywhere here is just n to the 1. So I divide everything here by n. N divided by n is 1, plus 1 divided by n is 1 over n, over n divided by n is 1. And this piece we just said is 0. Everybody follow that? So we renormalized. That divide top and bottom by the largest power of n trick, super duper important. Single most important technique for calculating limits of sequences. You'll use it in combination with all these other rules. Like you see here, I'm using the renormalization trick inside this problem where I've already done all sorts of other stuff. But you'll see this all the time. All right, now.
Wait, quick question.
Yes.
Is that equivalent to doing like n over n plus 1 over n?
It is, yep. Yeah, another way to say this is you can long divide n plus 1 by n, and you would get 1 plus 1 over n, as we did here. But there are settings where that division trick, or where splitting up the fraction doesn't work as nicely. Like if the denominator here was more complicated than just n, then I wouldn't be able to split that up in the same way. If this was like n plus 5 or n minus 3, then I wouldn't be able to get just 1 plus 1 over n. So you really do want to think about it as this renormalization trick. As n goes to infinity, 1 over n goes to 0. This is that same thing that we did over here. So this is 1 plus 0 over 1 minus 0, all to the 1/2 power, which is 1 to the 1/2, right? 1 plus 0 over 1, that's 1, minus 0 is minus 0. So this is the square root of 1, which is just 1. That's fine, Matthew. Yeah, you don't need 11 notes. Okay. All right. Any questions on this fella? As you get more practice with this stuff, these things will go faster. Yes, correct, Pablo. To renormalize any given piece, like to renormalize the n plus 1 over n piece, you divide top and bottom by the largest power of n. In this case, the largest power of n is n to the 1. Why not n squared? Well, because there aren't any n squareds here. So the goal with renormalizing, maybe this word is a little bit complicated if you haven't seen its use in physics. The word renormalize comes from a practice in astrophysics where you divide out in all of your expressions by the speed of light to essentially set the speed of light to 1. And then you use that as your metric. So the goal here is to get constants and things which go to 0. If you were to divide top and bottom by n squared, you would get 1 over n plus 1 over n squared, all divided by 1 over n squared. Well, then the top and bottom both go to 0. That's not helping me to understand what the sequence does. So you divide out by the fastest growing term. That will turn those fast growing terms into constants and all the other stuff into things which go to 0. Does that make sense? Yeah, so think of it as like trying to scale the function or scale the sequence so that the hardest to understand terms, the fastest growing terms, are under control. And then all of the slower growing terms will be replaced by things which go to 0, which allows you to see what the whole sequence is doing. All right. In the future, as you get a little bit more practice with these things, when you look at this limit, you'll be able to see quite quickly that this piece goes to 1 and that this piece goes to 0. And you would just be able to say, okay, the limit of the square root of this shit is equal to the square root of 1 minus 0. And you won't need to write all of these steps. But I wanted to go through this process to show you kind of where all those things are coming from. So practice writing things out very carefully using all of these steps. But then as you get more and more comfortable, I will allow you to get a little bit sloppy here. But for now, especially this week, and as you're working on the 11.1 homework, I want you to be very, very careful. Any other questions or comments on this problem?
It might be very elementary of me,
No,
but
it's up.
on the renormalization step, why can't you just cancel out the n and then leave it as 1?
Because there is no factor of n upstairs. So the question there, this is a good one, and I do see mistakes like this often. Is n plus 1 over n, can I cancel these? So what would we claim this to be equal to?
1.
So I would have,
1 over 0, actually. Yeah, you're right.
well, it's not necessarily that. When you cancel, the things you cancel are usually replaced by 1s. But this isn't kosher because n is not a factor of the top. So I see kind of bad cancellation all the time. This would be an example of that. Yeah, Damodar, that's Larisha, isn't it?
Yeah.
I like that. I haven't seen that in a while. I remember when she told me she does that. I like this. Yes, every time you cancel something like this, a cute, adorable kitten gets slaughtered. Don't kill the cat. So here's a good rule. You can cancel if and only if you can factor. The only things that ever cancel top to bottom are common factors of the top and the bottom. So if your previous step was not factoring the thing that you want to cancel out, then the cancellation is not kosher. That's the safe way to think about this. You can cancel if and only if your previous step was factoring out the thing you want to cancel. For example, here, if I had n squared plus n over n, I can factor the top as n times n plus 1, and I can factor the bottom as n times 1. Now it's clear that n is a factor of the top and n is a factor of the bottom, so this cancellation is okay. And the result would be just n plus 1 over 1. But if you did not factor in your previous step, you cannot cancel. That's the safe rule. And yeah, I do like Larisha's thing of every time you do this, you kill a kitty.
Yeah, let's not kill some cats. Thank you.
Let's not. No, kitties are cute.
I have a similar question about that problem.
Yes.
So for when you have n plus 1 over n, couldn't you also just split that up into n over n and 1 over n?
You can. And the result would be the same as this.
Okay.
So if
I was just like making sure that that was something that was allowed because it makes a lot more sense.
yeah, that's fine. In general, a plus b over c is a over c plus b over c because that's how fractions add, right? When you add two fractions with the same denominator, you get this guy. But if the denominator was a little bit more complicated, then the renormalization trick would be necessary. So for example, if I have n plus 1 over n minus 7, I could split this up as n over n minus 7 plus 1 over n minus 7. That would be okay. But now this piece isn't easy to work with. This piece is not n over n minus 7 over n or anything like that. Or n over n minus, I don't know, n over 7. None of this stuff works. So if you did have something like this, rather than splitting it up like that, the move is to divide top and bottom by n. You get 1 plus 1 over n divided by 1 minus 7 over n. And now if you had to take the limit of this, that's easy because this piece and this piece go to 0, so you just get 1 over 1. So splitting up the sort of simple rational expressions where the denominator has one term only, that's okay. But when you have a more complicated rational expression where the denominator has more than one term, this renormalization trick really is the best and fastest way to do things. In the cases where you can split the fraction up over its numerator, you'll get the same thing that you would get if you had renormalized. But there are also other cases like this where you don't get something nice if you split it up, but you do get something nice if you renormalize. So I really do want you guys to get comfy with the renormalization trick. Do you remember the rule that you learned in college algebra about horizontal asymptotes? Or maybe you learned it in pre-calculus if you didn't take college algebra, where you compare the degree of the top to the degree of the bottom, and then you get the ratio of lead coefficients for your horizontal asymptote? That's all proved using the renormalization trick. And the renormalization trick also applies to a lot of other things. So at this stage in your education, at this part of your getting good with limits, internalizing the renormalization trick is an important stage. It is something that we will need frequently in this class. So you can use other algebra tricks, that's fine, just make sure they're kosher. But also make sure you do get comfy with the renormalization trick because there are many places where it is the only thing, or at least the fastest thing that will work. It's been a good conversation. Thank you guys for asking.
I have a question about the problem.
Yeah.
So when you take the limit of n going to infinity of 1 times 1 over n, 1 over n goes to 0. Wouldn't you do 1 times 0 and that would just be 0? How do you get 1 plus 0?
These are added. These are being added. They're not.
Oh, okay. I thought it was a times.
Oh, yeah, I got you. Yeah. So
Okay.
n divided by n is 1 plus 1 divided by n is 1 over n. And then downstairs, n divided by n is 1. Yeah. So these are being added.
Okay, I see that. I was just, it seemed like a times sign instead of a plus.
Oh,
But now it makes sense.
That's just my bad handwriting. Okay. Any other questions on this fella? Okay, then let's try to get comfy with a few more of these theorems, a few more of these results. Oh wait, sorry, we haven't quite finished this one. So kind of ignoring this little bit here, what would we say about the sequence AN? Does it converge or diverge?
Converge.
Good. The sequence AN equal to the square root of n plus 1 over n minus 1 over n squared, we would say converges to 1. All right, so that's the language here. Remember, a sequence converges if it has a finite limit. All right. So let's calculate the limit as n goes to infinity of, how about the inverse tangent of 1 minus 1 over 2 to the n. What would my first step be here, and what result am I using to do the first step? Anybody see a place here where we could employ? I don't have a power theorem necessarily yet, nothing quite like that.
Would it be easier to make the 1 over 2n 2 to the negative n?
Something like that could be doable, but I think I've actually tried to write this in a way that'll make it as easy as possible. But there's something we need to do before we can get to work here. And that's to use our theorem on continuous functions to shove the limit inside. All right, so that's going to be my first step. The inverse tangent function is continuous everywhere. So I can take my limit from outside the inverse tangent function and shove it inside. And then I can split this up as a difference. So this will be the inverse tangent of the limit as n goes to infinity of 1 minus the limit as n goes to infinity of 1 over 2 to the n. Oh, I just needed the 1 close paren here, sorry. Now this first piece, 1, is a constant sequence. So as n goes to infinity, 1 just stays 1. What does 1 over 2 to the n do as n gets large?
I would say it also goes to 0.
Yeah, good, right? 2 to the n gets really, really big as n gets big, right? 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, 2 to the 5 is 32. So here the denominator is going to infinity. The top is just staying 1. And 1 over infinity, that's 0. So this is just the inverse tangent of 1. What is that?
Pi over 4?
Good. So this sequence converges to pi over 4, or the limit we were asked to calculate is pi over 4. And I want to talk about this piece for just a minute, because there are a few different ways people suggested thinking about this. One way you could think about this is as 1/2 to the n. Now we just showed that that piece goes to 0 because the 1 stays 1, the 2 downstairs gets big, and 1 over infinity is 0. So this guy is 0, and this is a special case of another very, very important result. Did anybody's pre-calculus class address geometric sequences? Can use the thumbs up react to show me here real quick, just so I get a feel. Thumbs up react if your pre-calc class discussed geometric sequences. Yeah, Sergio, I was gonna say. So I want to talk about those next. The renormalization trick is the most important trick for calculating limits of sequences. The single most important family of sequences, geometric sequences. So sequences of the form an equals some constant, we'll call it a, times some other constant r raised to the nth power are called geometric. The number r is called the common ratio. And what I'm going to do for you next is show exactly how all geometric sequences behave. It's one of the few times where we can look at this huge family of sequences and say what they all do. It's pretty cool. I'm going to give you the result. The limit as n goes to infinity of r to the n. This is why, remember, I was saying you need to read these as a sub n or a of n or just an so you don't confuse yourselves with powers. This actually is a power, r to the n. These can be broken down into a few cases. That limit is 0 if the absolute value of r is less than 1. That limit is 1 if r is equal to 1, right? 1 to the n is just the sequence 1, 1, 1, 1, 1. That's kind of boring. The limit is plus infinity if r is strictly greater than 1. And the limit doesn't exist if r is less than or equal to -1. So this theorem will tell us what all geometric sequences do. In other words, geometric sequences converge to 0 if the absolute value of the common ratio is less than 1, are constant if r is equal to 1, and diverge if R is, oh, I wrote less than or equal to here. I'm sorry, this should be, oh no, that was correct. God damn it, John. Less than or equal to -1. And diverge if R is bigger than 1 or less than or equal to -1. All right, so the language down here, what's written in words, is all a consequence of this limit here. And I'm saying this is a piecewise thing. The limit of this sequence depends on R. The special case of which we looked at in the problem above, 1 over 2 to the n. That's 1/2 to the n. So R there was 1/2. 1/2 has an absolute value which is smaller than 1. And so from this theorem, we could have said that the limit there is 0. We didn't need the theorem there because the numerator of R was 1, which makes it a little bit easier to work with. But in many other cases, these can be challenging to work with. All right, let's look at an example. Does anybody need more time to write here?
Yes, please.
Okay, I'll give just a couple more seconds. All right, I am going to go ahead and move on. I'll zoom out a little bit and move this up, so if you are still furiously scribbling. All right, so I'm going to give you the first few terms of a sequence, and I want you to sort out whether or not the sequence converges. The first few terms are 1, -2/3, +4/9, -8/27, and so on. So in order to do this, I would like to find a formula for the sequence an and then take its limit. So sort of two problems in one here, right? Find a formula and then take the limit and tell me whether the sequence converges or diverges. Does anybody notice any patterns here? I'm going to say the sequence starts at 0. So A0 is 1. A1 is -2/3. A2 is +4/9. A3 is -8/27. What sort of patterns do you notice?
The bottom's being multiplied by 3.
The denominator is being multiplied by 3 every time. Good. What's going on in the numerator?
The numerator is being multiplied by -2 every time.
So altogether, to go from here to here, I'm multiplied by -2/3. And altogether, to go from here to here, I multiplied by -2/3. And to go from here to here, I multiplied by -2/3. 2/3. So this is 2/3 to the 0. This is negative 2/3 to the 1. This is negative 2/3 squared. This is negative 2/3 cubed. AN is negative 2/3 to the n. We could have made this harder by having a constant out front, like 5, negative 10/3, positive 29ths, negative 40 27ths.
Why wouldn't the power be n minus 1?
Because I'm starting at n equals 0.
Gotcha.
If I was starting at n equals 1, then you could write it as an n minus 1. Geometric sequences, turns out they look a little bit nicer if you start at n equals 0. That makes your first term automatically just the constant term. So this is a geometric sequence with A, the constant, equal to 1, and R, the common ratio, equal to negative 2/3. So what can you tell me about the limit of this geometric sequence? I see two kind of agreeing claims in chat that the limit does not exist, that the sequence diverges. Why would the sequence diverge? So remember, we want to be carefully applying the logic of the theorems here.
I'd say it's 0.
Okay, so there's some competing ideas. Maybe the limit doesn't exist and the sequence diverges, or maybe the limit is 0, and that would mean that the sequence converges. Why do we feel one way or the other?
I mean, I see their point because it's a negative 2/3, but it's not less than or equal to 1, I think.
So the thing that matters here is this, right? This is the theorem that we can apply to get the result. Careful, Nathaniel, it sounds like you're trying to apply something from improper integrals to sequences, right? Remember that thing, like if one part of the integral diverges, the whole integral diverges. That's just improper integrals. Here with the sequence, there is only one part. It's just the AN. You know, this isn't like a multiple parts thing. And it's definitely true to have a big sequence that's built out of little sequences, where the little sequences together don't converge, but the big sequence altogether does. So the results from improper integrals don't work with sequences. We need to keep those things separate in our head. That's one of the big challenges in this part of the class, is to remember which theorems apply to which objects. That's why I recommend having those 3 separate pages in the back of your notes to try and keep organized which results apply to which objects. So Connor said something interesting, and I think it's kind of in line with what Sergio said. Connor, what is less than 1? Is it R itself that's less than 1 that I care about? It is true that negative 2/3 is less than 1. But specifically, what having to do with R needs to be less than 1 in order to give me something I can use here? It's the absolute value of R that matters, remember. The absolute value of R is the absolute value of negative 2/3, which is positive 2/3. And positive 2/3 is less than 1. So what's the limit?
0.
0. Good. So does the sequence converge or diverge?
It converges.
Good. The sequence AN converges to 0. All right. So this is a sneaky little subtle thing, and it's the first time you've had to use it, but I'm here to tell you, you're going to be using this shit a lot, like a lot. We're going to be using this result on geometric sequences, not just in the sequence sections, but also in the series sections, where they will be useful there as well. The objects we're messing with now are called sequences, and this is called a geometric sequence. There will be objects called geometric series, which are series that are built out of geometric sequences. And the result on geometric sequences will be used to prove something about geometric series. So we want to get very, very comfy with those. So good. Here, the sequence is geometric. And the absolute value of R is less than 1. Therefore, the sequence converges to 0, right? That's what we have here. In other words, geometric sequences converge to 0 if the absolute value of R is less than 1. So this is an important example. You'll want to refer back to this for several problems in the homework. Are there any questions about what we're doing here? I didn't actually take a limit like algebraically, did I? I didn't use any limit laws. So the theorem says that if the absolute value of R is less than 1, the limit will be 0. You get a DNE if R is not. I don't know if I can say it any more concisely than this, right? Yeah. So if R is bigger than 1, then the limit will be infinity. And in that case, the sequence would diverge. If R is less than or equal to -1, then the limit does not exist. Now, I think WebAssign puts these two into one box, because both of these are cases where we would say the sequence diverges. But there's a difference between saying the sequence runs off to positive infinity and the limit does not exist. However, in both cases like this, the sequence would be said to diverge. So yeah, if you have a negative number that is to the left of -1, then the sequence would not have a limit. The limit would not exist. So in other words, yes, what you said is correct. I'd like to give you a minute to try and think about why this is true, because it's so important. If you repeatedly multiply by a number bigger than 1, that makes things bigger, right? If you repeatedly multiply by a number between 0 and 1, like 1/2 or 1/3 or 0.12345, that makes things smaller. Every time you multiply by a number smaller than 1, you make the thing smaller. These geometric sequences are sequences where you repeatedly multiply by the common ratio, right? Every time here, I'm multiplying by -2/3. That's like multiplying by -1 and multiplying by +2/3 in every single step. So the multiplication by 2/3 makes the things smaller and smaller. The multiplication by -1 flips the sign back and forth. If your sign is flipping back and forth, but you're getting smaller and smaller and smaller, then you're still going to 0. So geometric sequences, regardless of whether R is positive or negative, will converge to 0 if the absolute value of R is less than 1. So it's the fact that r is small that says repeated multiplication by r drags you down to 0. You can kind of think about these as being like exponential functions where the base is small. So exponential decay. Stuff like y equals 2/3 to the x. You remember that the exponential functions have graphs that look like this if the base is smaller in size than 1. So as you run off to infinity, you're getting closer and closer to 0. Now here, if you want to think of it like that, my base or my common ratio is -2/3. I can't form a function like -2/3 to the x of the continuous variable x because the negative misbehaves when you raise it to powers like 1/2. But you can think of it as being an alternating exponential decay. All right, we're running short on time, and I have several other theorems we need to discuss. So I do want to get moving. But make sure you give that theorem on geometric sequences the respect it deserves. I'm going to give you 2 theorems and then show you a problem on which we can use them. This guy is useful from time to time. He says that the limit of a sequence is 0 if and only if the limit of the absolute value of that sequence is 0. The one direction is fairly obvious. If your sequence goes to 0, then the absolute value of your sequence goes to 0, because the absolute value of 0 is 0. But the converse, saying if the absolute value goes to 0, then you go to 0, that's a little less obvious, and that's useful sometimes. I'll give you an example in just a minute. First, though, the squeeze theorem. We should remember this from Calc 1, but in the setting of sequences, it looks just a tiny bit different. So if AN, BN, and CN are all sequences, and BN is trapped between AN and CN, and the limit of the outer guys are equal to each other, then the limit of the middle guy, say these are both going to L, then the limit of the middle guy is L also. In France, they call this the policeman theorem. They say if there's a policeman behind you and a policeman in front of you, and both of the policemen are going to the police station, then your ass is going to the police station as well. So an example to which we could apply either of these theorems is to investigate the convergence of the sequence AN equals -1 to the n over n. So here A1 is -1, A2 is +1/2, A3 is -1/3, A4 is +1/4, and so on. This sequence is not geometric because there's no constant I multiply by to go from one term to the next. And if you try to just take the limit, You could split this up as the limit of the top over the limit of the bottom. But the limit of -1 to the n, we've seen that a few times now. That's dne. And the bottom here is going to infinity. So this is not helping. Based on this, dne over infinity, I have no idea what's going on. But I've got these two theorems here. And either one could be applied to get me the result. If you look at the graph of our sequence, A1 is -1 down here. A2 is +1/2, A3 is -1/3, A4 is +1/4, A5 is -1/5. These look like they're getting closer and closer to 0, don't they? A6 would be +1/6, A7 would be -1/7. Those dots are definitely trying to get closer and closer to 0. So I could instead work with the absolute value sequence. We could say lim n to infinity of the absolute value of an is the lim as n goes to infinity of the absolute value -1 to the n over n. And then absolute values, they play real nice with division and multiplication. So that's the absolute value of -1 to the n over the absolute value of n. -1 to the n is either +1 or -1. All right, if n is even, it's +1. If n is odd, it's -1. Both of those have absolute value 1. So the top here is just 1. So I have lim n to infinity 1 over, and n here, n only takes values like 1, 2, 3, 4, 5. Those are all positive. So I get out that the limit of the absolute value of my sequence is the limit of 1 over n. I know the limit of 1 over n is 0. Therefore, by our theorem on abs values, the limit as n goes to infinity of the ans equals 0 also. So remember what our theorem up there says. It says that the absolute value of an going to 0 is the same as an itself going to 0. All right, that's what this theorem at the top here says. That you go to 0 if and only if your absolute value goes to 0. This is usually how we use that theorem. I have some sequence that I think is going to 0, maybe based on the graph, or maybe based on looking at the first few terms. But when I try to work with it directly, I get something that I don't really know what to do with. The reason I have no idea what this is doing is because the top has this dne, right? It's the -1 to the n part that makes this hard to work with. So instead of working directly with an, I work with its absolute value instead. The absolute value of an here simplifies to 1 over n. And I know that the limit of 1 over n is 0. So by our theorem, since the absolute value of my sequence goes to 0, my sequence itself must also go to 0. The other way to solve this problem is to use the squeeze theorem. I know that -1 to the n is always trapped between -1 and +1. So dividing everywhere by n, I get -1 over n is less than or equal to -1 to the n over n is less than or equal to +1 over n. And the limit of both of the outer guys is 0. Thus, by the squeeze theorem, the limit of the middle guy must be 0 as well. So the squeeze theorem and this theorem on absolute values, they're both very useful, but only in certain contexts. By far, the things that we use more often than anything else are the renormalization trick and geometric sequences. Very important that you remember both of those results exactly. The renormalization trick is something that we use sometimes as a part of other stuff. The result on geometric sequences is something that usually we use all on its own, which means you need to remember the theorem on geometric sequences to the T. These other theorems, the squeeze theorem, this absolute value theorem, they're cool. And there is one more cool theorem that I want to show you, but we're out of time for today. The last theorem that I wanted to show you is not something that you're going to find yourself using a lot, but thinking about the proof of this last theorem is one of the great ways to kind of help you understand intuitively what sequences do and how you can sort of wrangle them in, force them to do things that you want them to do. So if you haven't done, please read section 11.1. The theorem that we do not have time to discuss today is, so here you see them using the renormalization trick. Here you see our theorem on absolute values. Here you see the squeeze theorem. L'Hopital's rule is kosher, and we talked about this a little bit, although you haven't seen me do it. When we use L'Hopital's rule, we need to do this thing where you swap the n's for x's, and then you can use L'Hopital's rule just like you did back in Calc 1. It's the absolute value theorem, our continuous function theorem, the result on geometric sequences. All right, so the thing that we didn't have time to talk about here today is this definition, like monotone increasing, monotone decreasing, and this definition of boundedness. And here's the good thing. Monotone bounded sequences all converge. This is a cool theorem, but again, it's not super duper useful in the sense that it's not something that you use as a trick to compute limits. It's something that you can use to guarantee the existence of a limit. So I would like you to read this theorem. I would like you to read this portion of the textbook and make sure you understand it. There is one place, I think, in your homework where you'll want to make use of that theorem. And that's when you're trying to solve for limits of recursive sequences. Now, in those, you'll be able to assume that the sequence is bounded or monotone or whatever you need to do. But then you'll want to read through example 14 to see how you solve for the limit of a recursive sequence. It's very sneaky. Basically, you take limits everywhere in the recurrence relation. But again, this isn't something that you're going to see a lot of in this class. It's just a theorem whose comprehension will help you understand sequences better. So take a look at the pictures here and see if when you read the textbook, you can understand the definitions and theorems in section 11.1. Focus on the homework. One last note before I let you guys go for today is that next week I will be out of town for part of the week. So I'm going to be here on Monday. Monday of next week, we'll have our normal class. But then Wednesday and Friday of next week, I'll be pre-recording lectures. So you can watch those kind of at your own pace, but make sure on Wednesday you watch Wednesday's lecture, and make sure on Friday you watch Friday's lecture, and take notes. Because it's not a live lecture, it will be a recorded lecture. You're gonna need to like pause every now and then when you're still writing. I'm gonna have my normal office hours. I'll be bringing my laptop and doing office hours through that. So it's gonna be like a normal week of class for you guys. The only difference is that the lectures will be pre-recorded, so you don't need to watch them exactly at 9:30. But do yourself the favor of making sure you watch Wednesday's lecture on Wednesday and Friday's lecture on Friday. That way you can keep up with the pacing of the class. The material for next week is hard, all right? It's the first section on infinite series, and it is hard. So give it the respect it deserves. Don't fuck around just because the lecture isn't going to be live. And then remember, I will have normal office hours, you will have normal homework, everything is going to be like normal, except the lecture will be pre-recorded. That's for Wednesday and Friday. Monday's a normal class day. I'm gonna be here, you guys need to be here, everything just like normal. But Wednesday and Friday next week, the lectures will be pre-recorded. Any questions for me, Demeter? I see your thing there. Let me take a look and make sure everything is as it should be. I'll go through and clear those out. Anything else?
Will you have your office hour today?
Yep, normal office hour today.
Okay, thank you.
Any other questions? Alrighty then, you guys hang in there, keep working on that homework. If you get stuck on anything, do not hesitate to come by office hours or send me a Canvas message. That is it. Please read the rest of section 11.1. That last theorem, like I said, is not hugely important as far as computations are concerned, and it won't be coming with us into 11.2. It's just an 11.1 thing. But all the other results, the stuff that we covered here in class today, is important for 11.1 and for all the rest of chapter 11. So you really need to give it the respect it deserves. Infinite series and sequences are the reason people are afraid of Calc 2. So right now is the time to get extra serious. Make sure you put in the love here and you'll get through this class okay. Don't put in the love here, then exam 2 is going to be a dream killer. I don't want that to happen. So take care of yourselves, work hard. If you have questions, please ask for help, okay? I'll see you guys on Monday.
Have a good day, Professor.
You too, Saoirse.
Have a nice weekend.
You too, Ron.